He will talk about Oracle separation, query complexity, and BQP versus the polynomial hierarchy.
Thanks. Okay, so thanks for sticking around at this late hour, and thanks, Dorit, for inviting me for this great venue. So I will describe mostly a joint work with Franraz, but we will see some basic principles about Oracle separation, query complexity, and BQP we already saw, but we'll learn a little bit about the polynomial hierarchy. Okay, so I want to sort of just recall a few things that we already saw in Dorit's and Sandy's talks about, the doesn't work. Just a second. I can work with the. It doesn't work. Okay. Yeah. Okay. Never mind. I can use. This is. Yeah. Okay. Oh. Let me try it again. Okay, never mind. We'll make it work. Okay, that's surprising. All right, good, thanks. Okay, so I want to recall some of the complexity classes that were already mentioned. So we start with what we consider as efficient computation, or the class P, things that we can compute in polynomial time deterministically in the worst case. Right? This is what we consider efficient computation, at least classically. But we can sort of extend this notion. Instead of just wanting to get the answer correct on every input, deterministically we can sort of allow randomized algorithms or probabilistic algorithms. And then we just want to get the answer correctly with high probability, let's say 99%. Okay, and this gives rise to this class BQP that Dorit mentioned yesterday. And randomized algorithm seems to give us a richness. We get a lot more tools, algorithmic tools. But in fact, we believe that everything that we can do with randomized algorithm, at least for decision trees, we can actually de-randomize. So we believe that P equals BQP. So this extra power is maybe not giving us exact extra power, but so this is a big open question whether P equals BP. It relates to questions like P versus NP. We will not solve this question today, but at least this is a conjecture, okay, that P is equal to BP. Okay, so how can we extend it even further? So the next step is sort of is to consider quantum algorithms. This is the next step after probabilistic algorithms. BQP, the major topic for this week. And we know that quantum algorithms are capable of performing sort of amazing tasks. So Shor's algorithm is able to take a huge number and find its prime factors in polynomial time, whereas the best classical algorithm for that best known at least, takes exponential time. Okay? But can we prove that it must take exponential time? Okay, so that's on its own a very tough question. And all these classes that we talked about so far, they're all contained in P space, things that we can compute in polynomial amount of memory. Okay, so this, I think, the fact that BQP is in P space is in the problem sets. Okay, so let's now talk about a slightly different picture. So let's start with P again, but let's extend it in a different way to the class NP. Okay, so in P we need to sort of solve the problem efficiently. In NP we just need to verify that the solution is good efficiently. And there are many well-known problems such as satisfiability or the traveling salesperson that are known to be NP complete. Okay, meaning that if you solve any of these problems, you will solve all the problems in NP in polynomial time. And this is really the million-dollar question, whether P equals NP. So this is like the biggest open question in complexity theory. But in fact, these two classes, P and NP, are just the first two levels in an infinite ladder of classes called the polynomial hierarchy. Okay, so we have a ladder of classes, a polynomial hierarchy. I want to define it formally here. So how did we define NP? We said that the language is inside NP if there exists some predicate P such that we can, and this predicate operates on X and Y. This is very shaky. And we say that X is in the language if and only if there exists a Y such that P of XY equals 1. Okay? So Y is a witness to the fact that X is in the language. Once we are given X and Y, the predicate itself can be computed in polynomial time. So to verify that Y is a good witness, we can do it efficiently. But to find a Y, we don't necessarily have to know how to do efficiently. Okay, what about the polynomial hierarchy? So we said that the language is inside the polynomial hierarchy.
So you missed a line. I think you also need to define the soundness, not just completeness for NP.
So if and only if. So that's fine. Yeah. Okay. Okay. So that defines also this stuff. What about the polynomial hierarchy? So we sort of allow ourselves more power. So we can also talk about co-NP, and in co-NP we can allow ourselves to take for all statements. So we can check whether all Y satisfy the predicate. But what if we want to do more than that? So the general case is to allow predicates on X and several of these Y's, let's say Y1 up to Yk. Think of K as some constant. And this K will define actually the level in this ladder. And then we can check whether X is in the language by simply checking if there exists a Y1 such that for all Y2 there exists Y3. And we take K quantifier, so depending on whether this is odd or even, the last one would be either exist or for all. So I don't know, so something Yk. And then I apply the predicate on X and all these Yi's. Okay, so I can check whether there exists a Y1 such that for all Y2, the predicate on X, Y1, and Y2 holds. Okay, so this is like the richness of this polynomial hierarchy. And already in NP, we can sort of define thousands of interesting natural problems. And almost every natural computational task that you can think of sits within this polynomial hierarchy. So this is really a strong class that captures a lot of natural questions. We don't think that this is sort of efficient computation. We don't know even how to do NP, but we can think of it as some kind of upper bound on P or on NP. Okay. So still, this entire polynomial hierarchy sits within P space.
Can you give an example?
Yeah, so an example for, okay, so everything in NP is inside the polynomial hierarchy. If you want a more, something that you need like two quantifiers, so let's say that you want to minimize a circuit. So you want to give me a circuit, and you ask, is there a smaller circuit that computes the same function? So that's a exists for all kind of statement, because I need to show you a circuit, and then you need to check that for all inputs, our circuits agree. So that's a sort of canonical example, a circuit minimization. There are a few examples. There is like a book full of them, but I don't know. So this is the most natural one for me, at least. Yeah. In particular, you can say that the polynomial hierarchy contains BPP. Okay, so this is one thing that NP is not necessarily containing. And it contains also Merlin-Arthur that we discussed and Arthur Merlin. So it also contains interactive proofs where the prover sends us the proof, and then we do some kind of randomized computations. This is also can be described in this language. I mean, it takes a proof to show that you can describe it using these alternating quantifiers, but you can do that. Yeah. So any more questions? Okay. So you more or less all the classes except for BQP that we discussed is somewhere in this polynomial hierarchy. Okay, so the real question is, where does BQP fit within this picture? Okay, so we know that P is inside NP, inside the polynomial hierarchy, inside P space. Where does BQP fit? So we know that it's somewhere in between the small circle and the big circle, right? But what about the connection of BQP and NP, or the connection of BQP and the polynomial hierarchy? Is it true that one is containing the other? Or maybe they are just incomparable. Each one has its own strength. Okay? And this is actually a plausible hypothesis, that all these containments are false. That all these 4 containments are false. Okay, so let's say that you believe that these containments are simply not true. Can you prove that? So, can you? I would be surprised. Why? Because to do that, you need to come up with some language that is in one of these classes and not in the other. So you need to come up with some language that is, let's say, in NP but not in BQP. In particular, this language would be in P space but not in P. So any separation would, in particular, would have to separate P from P space, and this on its own is this huge open question in complexity that we have no clue how to solve. So this is sort of at the scale of P versus NP. So to just show that any 2 of the classes that I discussed so far are different would imply that P is different than P space, and this on its own is a huge open question. So as far as we know, all these classes are equal to P. That's okay, so that's it. So what do we do now? Okay, so I want to say that the motivation for this talk is we want to sort of understand where does quantum gives us an advantage. Okay, where does quantum computation give us an advantage? And it seems that in this Turing machine world, unconditionally, it's hard for us to show these results because we need to separate P from P space, and we need to sort of relax the question. We need to move to a slightly different model. Okay. So what we're going to turn to the help of oracles. Okay, so what do I mean by that? What is an oracle? You should think of an oracle as some kind of black box or subroutine that might or might not help you in the computations that you're trying to execute. Okay, so let me give you an illustrating story from Terry Tao's blog, and this would sort of demonstrate maybe what is an oracle separation. So Terry writes about 2 students named P and NP that he has. And Terry wants to tell which student is wiser. But it's hard to tell. You know, he gave both of them projects, but despite working long hours, they don't come up with any results, and no new theorems, no new papers, nothing. Okay. So he comes up with an interesting idea. He gives them access to a supercomputer. Okay, and they have access to this. After a week, he comes back to the lab, and he sees that NP, she produced 10 papers. She solved 10 big open questions, and all the proofs are correct. And now P is still stuck. P is still struggling and trying to do something new. So this gives us evidence, maybe partial evidence, that NP is wiser, because with this additional resource, with this supercomputer, she was able to produce results that P was not able to produce. So this is sort of what we will try to capture. Okay. So how do we do it formally? An oracle is just this subroutine, or you should just think of it as a function. You give it a string, it tells you yes or no. What does it mean, yes or no? It just tells you for some string yes, and for some strings no. And you can treat this oracle as an additional resource. You can ask questions to this oracle, And the oracle would give you the answer within the next time step. So it will take in 1 second to answer. And with respect to an oracle A, you can redefine the power of all the classes that we talked about. So you can redefine P, NP, the polynomial hierarchy, and so on and so forth. So let's see an example. So let's recall the definition of P. So there were a few definitions, but I'm sticking to the one with Turing machines. So a language is in P if there exists some Turing machine that runs in polynomial time and can decide whether or not a string is in the language. And it's inside P to the A. Similarly, but the Turing machine can also ask queries to the subroutine A. So you can always call this function A, and the function would return you an answer. Now, maybe this answer is not helping you at all, but for some cases it will. And the idea is that the oracle would help, let's say, NP solve some tasks, but P would still be unable to solve this task with respect to the same oracle. Okay. So oracle separation have a long and rich history, and this beautiful line of work shows that you can actually separate all these classes relative to an oracle. So once you introduce an oracle, you can separate P from NP, NP from the polynomial hierarchy. In fact, you can separate all the levels of this infinite ladder, and you can separate the polynomial hierarchy from P space. So this is in the classical world. What about relations between quantum and classical world? So the seminal result of Bernstein and Vazirani is that introduced BQP to the world, showed that relative to an oracle, quantum polynomial time is stronger than probabilistic polynomial time. You can solve certain tasks in quantum polynomial time, but probabilistically you'll need super polynomial time. And then Simon showed that for some problems you even need exponential time probabilistically. So there are exponential separation between the power of quantum algorithm with respect to an oracle and the power of probabilistic algorithms. What about BQP and NP? So these two results show that they are likely incomparable. So relative to some oracle, there exists a task that quantum can solve efficiently but is outside of NP. And the same goes to the other direction. For another oracle, there exists a task that NP can solve, whereas quantum polynomial time cannot. So this shows us about the power of quantum computing. It can go beyond NP. And this shows us about its limitation. Quantum polynomial time is unlikely to solve all of NP, and in particular the NP complete problem. So you can view this as some kind of evidence towards this belief. Okay? But why do I say evidence? Because recall that this is with respect to an additional resource. It doesn't mean that this is the case once we remove the additional resource. And we know that there are a few examples where two classes are the same, but once we introduce a different resource, they suddenly become different. So some equalities or inequalities do not hold with respect to an oracle, but others do. So for example, all the containments that we showed so far work with respect to every oracle. Okay. So the motivating question for this work was, how far can quantum go? So this was asked by Bernstein and Vazirani. We already seen that quantum can go beyond BPP and beyond NP, but can it go beyond even this entire polynomial hierarchy, this infinite ladder of classes? Or maybe BQP sits within this ladder. Maybe you can express everything that you can do in BQP with, 4 quantifiers. For example, for BPP, we know that you can express everything in BPP with 2 quantifiers. Okay. And our main result is that
what is a quantifier?
This is a quantifier. There exists or for all. Yeah, I should say that each one of these quantified yi's are strings. So you should think of these yi's as strings of length polynomial in the length of x. Okay. Okay, so our main result is that relative to an oracle, BQP can be stronger or can perform tasks outside the entire polynomial hierarchy. Or pictorially, you have this P inside NP inside PH, and we show that relative to some oracle, there exists some task that BQP can solve, but this task is not in PH, not in NP, and not in P, relative to the same oracle. Okay. So I want to give one interpretation of this result. So this is a quote by Lance Fortnow. He says, even if P were equal to NP, even making that strong assumption, that's not going to be enough to capture the power of quantum computing. So let me explain this sentence. In this weird world where P equals NP, so we sort of believe that P is different than NP, but let's even assume that P equals to NP. What would happen? The entire polynomial hierarchy collapses. So everything in this polynomial hierarchy can be computed in polynomial time, classically and efficiently. Still, in such a world, there could be problems that could be solved by a quantum computer efficiently that cannot be solved classically efficiently. So BQP still might have an advantage even if everything here collapses to P. Yeah.
Can you give, just to give intuition about this oracle notion, can you give an example for a case where two classes were the same even though they were different with respect to an oracle? And also, did this ever happen for classes where you know they're different with respect to random oracles?
Yeah. So there is sort of like one example, which is so this was mentioned briefly. I don't know if I want to get into all the definition exactly, but there's a famous theorem that IP equals P space. Okay? And before this famous theorem, there was an oracle separation showing that, even co-NP is not in IP relative to some oracle. So in particular, P space is not even in IP relative to some oracle. So what does it tell us? It tells us that the proof that IP equals P space is sort of like a non-relativizing proof or a non-black box proof that sort of, that sort of looks into the black box. And okay, this will maybe mean more once we looked into the query model. But a lot of the techniques that we are using are black box techniques. So when we simulate, I don't know, BPP, we fill the polynomial hierarchy, this is sort of a black box technique. When we say that P is inside NP, this holds with respect to any oracle. So it's true that it's not sort of like bulletproof, but I view it as some kind of evidence towards the true answer. Right, and I think this also holds with respect to a random oracle. And this was like the first. So there was this conjecture that if things would work with respect to a random oracle, then they hold in the real case, and this was sort of refuting this conjecture. Okay. Actually, I have an open question about this at the end. So, if I
you hint about the problem that you probably presented the problem, right?
Yeah. So we will talk about so yeah. This will be the topic. Like this result will be the topic of the entire 2 hours. So you will see the problem in details. Okay. So I guess it will be good now to move towards the problem. But before that, I want to slightly change the model and sort of restate our result. Okay, so I want to restate our result not with respect to oracle, but in the language of in the query model that Adam introduced yesterday. Okay, so let's look just on the oracle. Yeah.
I don't know if the question makes sense, but can you also show a separation with respect to like an algebraized oracle, like an oracle where you also get access to the low degree extension of the function or something like this, right? This is sort of minded by this example, right?
So I mean, you could try to do that. We haven't tried with respect to this thing. So the question was, so this is sort of digging into this IP equals P space. So the problem here, why this does not hold with respect to an oracle is that you can also sort of ask the oracle questions not on what it was supposed to to answer, but also on some kind of algebraic extension of the field that it was supposed to answer. So instead of asking it on 0, 1, you would ask it on, I don't know, 0, 1, 2, and 3. Okay, so you are able to have these weird access to the oracle. And if you can prove, and you can prove that IP equals P space sort of relativized with respect to these additional queries. So then you could ask for separations that hold with respect to these oracles. So we didn't try to do that. So, yeah. Okay. All right. So I want to move sort of to the black box model. I find it sort of a little bit more intuitive. So the oracle sits in this black box, right? So let's just focus on the interaction that we have with this oracle. So we are asking the oracle some questions, and we are getting some yes/no answers. So for simplicity, I'm going to assume that all the questions that we make to the oracle during the running time of the algorithm are of the same length. Let's call it little n. Okay? So how can we describe the behavior of the oracle? It's just a function. For every possible question, we can say whether the oracle answered yes or no. So we can just write the behavior of the oracle as a truth table of length 2 to the little n, just specifying for each possible query whether it tells you yes or no. So I'm going to denote the length of this truth table by capital N, which will be exactly 2 to the little n. So now think of this truth table, this huge truth table of length capital N or exponentially little n, sitting inside the oracle, inside this black box. And how do we access this black box? We're just going to ask, what's the ith entry of this truth table? We're going to get an answer back. What's the jth entry? Answer back, so on and so forth. So we can maybe ask these questions adaptively. So based on the answers that we got, we can maybe ask new questions. And each time we make a question, we get the ith. We get 1 bit of information from this black box. And in this model, a typical question that we would like to answer is, we have this black box and we want to say, does the string x satisfy some property or not? And we want to determine it by making as few queries to the black box as possible. So we want to ask maybe, I don't know, log capital N many queries and say whether the string has some property or doesn't have this property. Okay. So we're going to consider efficient computation as things that run in time polynomial in little n, okay, which is really polylogarithmic in capital N. Okay, recall that capital N is exponentially big. So we really want to sort of tell whether the string has a property or not super efficiently in times which is polylogarithmic in the length of this truth table. And this is what we consider as P. Okay, so this will be the analog of P. We can also talk about the analog of BQP, and then we allow ourselves randomness, and then we are asking a question, getting an answer back. Maybe we allow ourselves to flip coins between successive queries. Okay. What about the quantum analog? So we can also consider the quantum analog of this model, but then we want the black box to perform a unitary. So this was introduced in Adam's talk. I'm going to use a slightly different way of that, a slightly different notation. So I want the unitary to map this state I to I multiplied by either plus or minus 1. Okay, depending on the ith input of the truth table. Okay, so notice that this preserves norms, and I can naturally extend it to a linear transformation, and this gives me a unitary. And if I think of it as a matrix, it's just a diagonal matrix with 1s or minus 1s of the diagonals, depending on x. Right? So this is just one query, and once we define it over the standard basis, we obviously have it over superposition over the standard basis. So if we give it a superposition over queries, we get a superposition over answers. So this is just one query. And then what can we do in general? We are applying a query. Then we do some unitary transformations that does not depend on x. then another unitary, then another query, then unitary, and so on and so forth. But we still want the number of gates that we are applying to the state to be polylogarithmic, and we want the queries to be, the number of queries to be polylogarithmic. Okay, so this is the analog of BQP. What is the analog of the polynomial hierarchy? Well, this turns out to be a very well-studied class of circuits called constant depth circuits. So these are just circuits composed of constant many layers, where each gate is either or AND of the previous gates, and we have variables or the negation at the bottom. If you're not familiar with this class, we will see it in detail in a few slides. But basically, the idea is that you sort of translate this expression into a circuit. So you replace every OR, there exists with a huge OR going over all possibilities of the yi's. Every for all you replace with a huge AND. And you replace the predicate with an OR of ANDs. So this way you go from this, k quantifiers, you go to a circuit with, I don't know, k plus 1 many layers. Okay, so we define the analogs of all these classes that we saw so far. And what we'll show is we'll separate the analogs. We'll separate the analog of BQP from the analog of PH. And then, by non-reduction, this implies oracle separations. Okay, so this is actually how we prove the oracle separation. But even without this reduction, I claim that this is sort of interesting in its own right, because what this model really captures is the ability to extract information from a black box efficiently. So what we'll show is that there exist some properties that quantum algorithm can extract efficiently whether the property holds or not, whereas classical algorithms cannot. And we will even show that even classical algorithms that have the superpowers of the polynomial hierarchy cannot extract this property.
Sorry, I
Yeah.
don't understand this analogy. Why is AC0 analogous to PH, and what are you planning to prove? I'm not sure I understood this outline.
Okay.
So, you're saying analog is a formal analogy or just sort of conceptual?
Formal, yeah. So I'm saying with respect to the oracle.
Could you repeat the question?
Yeah.
Most of the questions I didn't understand. The slide.
So the question is, why is the analog of the polynomial hierarchy AC0? Okay?
What do you mean by AC0? AC0 which access to the oracle?
Okay, so let me start. So we discuss everything with respect to an oracle. So PH with respect to an oracle A is just this thing, where the predicates can also access A. Okay, so that's PH with respect to an oracle A. Okay, so how do I write this as an AC0 circuit? That's a good question.
Just AC0. That's the correct.
Yeah. So I want to check this expression. So what do? I just take a huge OR over all possible y's, over all possible values for y1. Okay, how many do I have? It's 2 to the poly little n. Right? But recall the oracle is of length 2 to the n. So this is not so bad. Okay? And then I take an AND over all possible y2s. And here I have also 2 to the poly n. Okay. And so on and so forth. So each gate is sort of has a big fan-in, this big. And in the end, I apply the predicate on x and all these yi's. Okay? So actually, you should think of x as fixed. The only thing that is not fixed is the oracle. So think of how would the secret look like for an x, which is the all ones string, let's say. Okay? So in the end, you are making some queries. So in the end, you need to replace this thing. The predicate that works in poly n time and makes access to the oracle A. How can you write this thing? You can write it just as a decision tree. Okay? So this thing you can write as a decision tree. of poly n many, of poly n depth, and any decision tree of poly n depth you can also write as an OR of n's, where this is 2 to the poly n, and this has poly n. Okay, so I just sort of translated this into an OR of n's over the answers of the oracle. And overall, what you get is you get a circuit where the input depends on the answers of the oracle, whether the oracle what the oracle answers on every particular query that we can ask. And then how do we propagate these values upwards? We're taking ends of them, and then ORs of them, and then ends of them, and ORs of them. Eventually, we are getting the answer, whether or not X is in the language. So this was, yeah, I'm sorry, this was a little bit fast in case you're not familiar with these things. And it seems that this transformation is sort of, very inefficient because everything is exponential in poly of little n. But notice that the length of the input is sort of also exponential in n. So this is really sort of quasi-polynomial. Okay, so this is, okay, so capital N was 2 to the n. So if we think of the size of this circuit in terms of capital N, this is something like capital N to the polylog capital N size and constant depth. Yeah, I mean, okay. So I'm sure that most of you didn't follow it. So I'm just going to say, ignore this connection, just believe me, and we'll talk about AC0, and we'll just want to show that, things that you can do in quantum logarithmic time cannot be done using AC0. So that's our goal. Okay, and how this translates to oracle separation is sort of not the main focus of my talk, but yeah.
So the AC0 you're saying here can have gates like the black box, but like the gates can be a black box. Is that what you mean with AC0? Like,
Yeah, maybe just define AC0 because I'm not sure. You did, right?
I didn't, because I wanted to do it later. I can go into it. Okay, so this is AC0. These are circuits composed of ANDs and OR gates, where you have variables or the negation at the bottom. And you'll think of two parameters you'll concern. S would be the number of gates in this circuit, and D would be the number of layers in this circuit. Okay, here the number of layers is 3. Okay, we are considering how many layers of gates we have. And on the bottom, you should think of the bottom as all possible values of this huge string, this oracle string. Okay, so this oracle string of length capital N or 2 to the little n. So just think of each bit here representing the output that the oracle would give on this particular query. Okay, so that's how you should think about it. Yeah.
Just want to ask that AC0 needs to be constant depth, but the predicate of pH could be polynomial depth?
No, so pH is sort of, I'm allowing only constant many queries. Okay, so the number of quantifiers. The number of quantifiers does not depend on the input length. So pH is really the union of what you have with one quantifier, what you have with two quantifiers, what you have with three quantifiers, and so on. So it's a union of all these classes, and each level has fixed number of quantifiers.
So it means if I want to unroll the predicate for pH formula into a AC0 circuit, it will be constant depth?
Exactly. So when I'm translating it, each one of them translate to to one sort of layer, and then in the end the predicate translates into 2 layers. So if I'm taking, I don't know, 5 quantifiers, then this would translate into a circuit of depth 6.
Another question is,
Or 7.
what about the number of fan-in? Would that be exponentially large?
So the fan-in is unbounded, so you can take the fan-in as large as you want, but we will bound the size. So in some sense, the fan-in is bounded by the size, right? So you can only take or AND of all the previous gates. Okay, so yeah. Okay, so any more questions?
If you go back to that slide, it's still not clear what it means. I mean, what's that pH analog? What's that? And then it's equal to AC0, which we define now, but maybe it's trivial.
It's not trivial. This takes a lot of time to process.
I mean, let's say, when you say the quantum analog, what do you mean by that?
I mean, okay, so you can just look at all these classes, BQP, P, pH, all these classes, you can look at them in this query model. Okay? And then you can ask, what is the analog of P? The analog of P is everything that you can do in the query model, is everything that you can do in poly little n time with access to this oracle, or with access to this black box. So you can also, so each time that you query the black box, this counts as one time step. And in quantum polynomial time, again, you can do everything that you can do in quantum polynomial time, but you can also access this black box. But notice that there are this, maybe what's confusing is that we are thinking of polynomial time in little n, whereas the description of this truth table is exponential. Yeah. Okay.
So I just said that the analog of pH, I mean, just pH with query to the
pH with query to the oracle is captured by AC0. So you can sort of translate everything. Yeah. AC0 without an oracle. Exactly. Yeah.
This is true for any other thing? Like you said, pH with some volatility. Is this what you can have any arbitrary volatility of the pH with that volatility same as AC0?
So the question is whether I can translate any oracle, pH with any oracle, to an AC0 circuit. Yes, so the oracle only determines the input to the circuit, in some sense. Right? So the oracle just describes the input to the AC0 circuit. Okay. All right, so yeah, so this is quite a confusing slide, and this is a lot to process, but basically what I want to say going on forward is that you could sort of forget about oracles and just focus on these circuits and what you can do with what you can do super efficiently with quantum algorithms. That's what our focus would be. The fact that this implies this oracle separation is nice to have, but I want to focus more on the query model. Okay. So now I want to define the task. So now I want to get to the problem that separates these two models. Yeah. Right. Right. So now there's no input. So I sort of like hide behind the rug the fact that I sort of ignore the fact that I usually have an input and I want to compute something on this input and I have access to an oracle. Now I sort of ignore the input and I only think of the oracle, and I'm trying to just extract some information from the oracle. So you can think of it in the story that I told earlier as if on the supercomputer were some hidden files, and the only thing that NP did is sort of like guess the password, and then she could read the input. So maybe it's impossible to do what NP did without access to this oracle, because he really just extracted the information from it. And right. So in oracle separation, sometimes the problem itself doesn't have any meaning without the oracle. So sometimes you would just ask to solve undecidable languages, and with respect to the oracles, they will be decidable. So yeah, so I agree. It's a little bit of a weird setting, but I think the query model is more, I like it more because it's sort of like you have this black box and you want to extract information from it. Yeah.
Can your language define the oracle?
The language and the oracle will be sort of coming together. So the language can depend on the oracle, for example. Yeah. Okay, so what will be the task? So we want to show that for some task, quantum algorithms that work super efficiently can extract information that probabilistic algorithm cannot. So this was suggested by Scott Aronson, and he suggested the following game. So we would sort of construct two black boxes. In one, the truth table would be sampled uniformly at random. Okay, so this truth table would be just a uniform random string. And on the other hand, on the left-hand side, this truth table will be sampled from some other distribution called the forrelation distribution that we denote by D. So we have these two black boxes. I need to tell you some things about this distribution, but just think of it as some arbitrary distribution that is not the uniform. So it has some pairwise correlation. It has some correlations between the indices. Okay. So now you have these two black boxes, and an adversary comes and picks one of them at random and hands you the black box. And you need to tell which black box you got. So that's the game. And you need to tell which box you get. So you then get to see whether it's written U or D here. But what you're able to do, you're able to ask questions to this black box. So you're able to ask, what's the first entry? What's the seventh entry? Okay? And you need to win this game. So with respect to this game, we will show the quantum advantage. So Scott Aronson showed that super fast quantum algorithms that work in time polylogarithmic in capital N can tell the difference between the black boxes. They would answer here U with high probability, and here D with high probability. So they will know the difference. On the other hand, what we'll show is that AC0 circuit cannot tell the difference. They behave very similarly on this black box as they will behave on that black box.
What is the goal? When do they win?
They win if they could identify whether it was U or D. Okay, so they win if they could.
They choose.
The adversary comes. So let's say first you sample both of these black boxes, and then an adversary comes and gives you one of them. So you don't know which one you got, and you need to tell whether it was the one from the left or the one from the right. Okay? Okay, so I need to define this distribution D, right? What is this correlation distribution? So the idea is, the idea behind the distribution comes from the very useful fact that comes to play in many quantum algorithms, that you can apply the Hadamard transform very efficiently, right? So if you want to apply the Hadamard transform on n over 2 dimensional Hilbert space, you can do it in logarithmic time using quantum gates. So based on that, we would want to define our distribution. And the thing that I want to capture about this Hadamard transform, this is a linear transformation, so we can just write it as a matrix, and the ijth entries are sort of captured by this either plus or minus 1 divided by square root n over 2, because I think of vectors of length n over 2, you will see soon why. So what I want to emphasize is that the entries of this orthogonal matrix are very small. Like each entry individually is very small, and this would play an important role in the proof. So with that in mind, let's define for two vectors, x and y, their forrelation as you take the Hadamard transform of X and then take correlation with Y. Okay, so you apply Fourier and then correlation, therefore forrelation, the name suggested by Scott Aronson. And what will be the task? You need to tell the difference between two cases. In the uniform case, the strings X and Y will be chosen uniformly and independently of one another. In particular, they would have sort of small forrelation with high probability. And in the second case, in the case D, you're selecting strings X and Y in a way such that with decent probabilities, their correlation is large, is at least n over log n. Okay, so you're selecting strings that are very correlated here, and here you're selecting strings that are not so correlated. So these are the two distributions. You can also sort of change the problem a bit and define it over a promise problem where you know that either the correlation is large or it's small, but I prefer to talk about these two distributions because it's a little bit easier to deal with that.
Properties for any two strings in the distribution?
Sorry, can you?
This property is for any two strings in the distribution. You want them to have small correlation, or?
So this is really a promise problem. I'm sort of promised that either the strings are sampled from the uniform or from the distribution D, and I need to tell the difference. So if the strings were sampled from some other distributions, then I don't need to decide. And when you translate it into this sort of not distinguishing game, but rather you get two strings, and you know that either the correlation is very small or very large, and you need to tell the difference. But if it is somewhere in the middle, I don't care.
So the black box emits each time a pair of X and Y for any given input? Is that?
No. So the entire black box can be described by this X and Y, and then we are querying individual coordinates in these vectors. Okay, so the entire oracle, the entire truth table is these two vectors.
It's actually one vector, which is just the first half of it is X and the second half is Y.
Exactly, yes. I think, yeah. So, yeah.
Does the algorithm of Scott works for any correlated string?
Yeah. So the algorithm so the question was whether the algorithm works for any correlated pairs. And yes, we will see that actually the algorithm can sort of estimate this correlation value. So if the correlation value is high, it will accept with high probability. If it's low, it could sort of reject with high probability. Okay, yes, another question?
Is that assumption correlated norm larger than n over log n? Is that with high probability, or each time you will get that Boolean string?
So this is, so we will, okay, yeah, I will not show this exactly with high probability. I will show that this holds with probability roughly 1 over log n. But nevertheless, I will show that with high probability over the sample, it's indistinguishable. Okay, so that's, or in other words, I'm so that the expectation here is very similar to the expectation here when I'm looking at the circuit. Yes. Okay. So yes. Yeah, so you can specify, the question was, how can you query the oracle? So you just need to specify, a coordinate of the oracle, and then you get an answer back, right? Okay, so that's very, very similar to earlier.
The answer is a string of 0, 1.
Every time you query a coordinate, and you get 1 bit. What's the value of this string, of this coordinate in this string?
But you can't even point at the coordinate.
Why not? To point takes you n bits, little n bits, or log capital n bits, right? So that's considered efficient still. Okay, yeah. No, so I didn't define. So this is sort of like a sketch. So I didn't define D yet.
Correlation is a distribution, isn't it?
It will be, but so far I just defined this inner product, and I just said that I will sample pairs that have high inner product, but I didn't say how. So I need to specify how I'm sampling. Okay, so it's not clear. Maybe there are no vectors with high correlation value, for example. Okay, so you could say that you are sampling them from all possible vectors with high correlation values, but I would not want to go into this direction because then I don't know how to analyze that.
No, but I thought that you're comparing between two. One distribution is uniform and another distribution.
Yeah.
I thought that you choose a certain distribution.
Right, I am choosing it. I just haven't defined it yet. I want to do it in the next slide, okay? Yeah, so maybe let's define the distribution and then maybe we'll continue tomorrow showing the fact that, quantum can win the game and classical fails to win the game. So the fact that these entries would be small would be crucial to show that this distribution has a very small pairwise correlation, as we'll see next. Meaning that if you look locally at this string, if you look at a few locations, 2 locations, 10 locations in these strings, it's hard to tell whether this was sampled from the uniform distribution or from this correlation distribution. So local views are sort of similar. And based on that, we will show lower bounds on the classical algorithms. Nevertheless, the quantum algorithm is able to use this global property that these strings are correlated because it can apply the Fourier transform very efficiently. So it can query things in superposition, apply the Fourier transform, and therefore sort of can tell whether we are in this case or that case. And we will see this tomorrow. Okay, so I want to define the distribution. This is okay. So this is the plan for the rest of the talk. So we want to define this distribution D, formally define it. So far we just wanted to sample correlated pairs, but we didn't say how. Then we want to show that there exist some quantum algorithms that distinguish D from the uniform distribution. And finally, we want to show that any AC0 circuit doesn't distinguish, meaning that the probability that it would accept a string sample from this distribution is similar to the probability that it would accept a uniform string. Okay, so that's what we'll show. Eventually, this would be the most technical part. Okay, so how are we gonna sample correlated pairs? So how are we gonna define the distribution D? So this is based on the suggestion made by Scott Aronson, but with a few modifications. So I'm gonna first define a Gaussian distribution over n dimensions, over Rn. And then I'm going to I'm going to make it discrete and going to generate a distribution over all strings of length n over plus or minus alphabet. Okay, so how I'm going to start? So I want to first define this Gaussian distribution G. So I'm going to just sample x1 up to xn over 2 IID Gaussians with mean 0 and variance sigma squared. Okay, so x1 up to xn over 2 are just, independent Gaussians, identical. And then I'm going to take this vector of x's and I'm going to multiply it with the Hadamard matrix. So I get a new vector of y's. And then I'm just going to take the concatenation of the x part and the y part. So this will be sort of my string. But this is not really a string because each number here is really a real number. Okay, so I need to specify this variance. So I didn't take the standard setting where you pick the variance to be 1. I pick it to be roughly 1 over log n. And the reason is that I want all these numbers, I want them to be with high probability within -1, 1. So each of these coordinates individually is distributed as a Gaussian with mean 0 and variance sigma squared. And you know, and you can tell by tails of Gaussians that if you pick the variance to be 1 over log n, with high probability, all these coordinates will be within -1, 1. Okay, so that's, yes?
Is the x1 the bit or a real number?
So far we defined a way to get real numbers. So far this is not really a discrete object. So now I need to tell you how to make it discrete. Okay? So this gives us n real numbers. How do I make it discrete? So there are two suggestions. So Scott's suggestion was just, take the signs of these coordinates. So we don't know how to analyze that, actually. So we did something else. So we draw this vector z according to the Gaussian distribution, and we check, is this vector within the box -1, 1 to the n? Are all the coordinates between -1 and 1? If not, then I don't know how to handle this case, so I just abort. Or maybe output a default string. But you shouldn't worry about this abort option because, as we said, with high probability, this would not happen. Okay, with high probability, all the coordinates would be within -1, 1. So just think of this case as just this thing doesn't happen. Okay, so now I got a bunch of numbers between -1 and 1. How do I get plus -1 random variables? So I'm just going to treat these z1 up to z. Okay, so this is the vector of z's. So I'm going to treat this vector of z1 up to z capital N as biases of coins, and I'm going to flip coins independently with these biases. So z prime I would be a plus -1 random variable whose expectation equals the value of zi. So let's say that z1 was 0. How do I draw this z prime 1? It's just half-half, right? So with probability half, it will be 1. Probability half -1. Therefore, its expectation would be 0. And if z7 was 0.9, then with probability 95%, I would pick 1, and 5% I would pick -1, and the expectation would be 0.9. So I can always do it if the numbers are between -1 and 1. And okay, so now it's an exercise since we are running out of time. And okay, so when you sample these Gaussians, you can see that the forrelation is big, right? Because y equals h of x. So in fact, the forrelation is just the norm of h of x, which is large. And the idea is that when you do this randomized rounding, the forrelation is more or less stays the same. So the expected forrelation under this distribution D is very similar to the expected forrelation under the Gaussian distribution. Okay, and you can work it out if you sort of ignore this abort. So if you ignore this abort, then this is very easy to see. With this abort thing, then this becomes complicated. And there's a problem is the problem set that more or less asks this question. Okay. All right. So this is a way to sample forrelated pairs, or at least in expectations, their forrelation would be large. And tomorrow we'll see that quantum algorithms can tell the difference between this distribution D and the uniform, whereas classical algorithms cannot. Okay. So thank you.